that we depolarize the membrane rapidly due to sodium influx. Calcium channels are open, those L-type calcium channels are starting to open, and we maintain the length of that depolarization due to that calcium influx. So this is due here, this plateau. This is due to the ECF calcium, not the sarcoplasmic calcium. And the reason it stays longer is because it takes longer to pump back out. Eventually, though, it starts being pumped back out, and at this point in time right here, these slow-acting voltage-gated potassium channels are open, so potassium is diffusing out of the cell, and we're pumping calcium back out, and as a result, we're going to repolarize the membrane. Now, if you look at the length of this, right, here, if you were to look at a typical action potential on this one, it would look about like this. Depolarize, repolarize, hyperpolarize. Okay. So that's pretty quick, right? This is what an action potential looks like on a skeletal muscle or a neuron. Real quick. That's 4 or 5 milliseconds. This one, on the other hand, stays depolarized 250 milliseconds. And the significance is this. What do muscles do in response to action potentials? They contract. So there's a latent period, then there's a period of contraction, and then there's a period of relaxation, and they're back to rest. Okay. Now, if this, and that's the same twitch in both cardiac and smooth because they have sarcomeres, they respond the same. So the twitch looks very similar. However, what happens here, rapid action potential, latent period, period of contraction, period of relaxation. You could get another action potential here, right here. Right? It's already had one, you could have another one. And if you did that, this would then just keep contracting up to tetany, and then it would fail. Right? But here, in response to this one, when can you get another cardiac action potential? Not till out here. Not till you get repolarized back below the threshold out here. So as a result, when you get another action potential right here, the muscle cell's already relaxed. So what does it do again? Contracts and relaxes. You never get this summation. And I know we didn't talk a lot about what causes fatigue and failure, but you will not pass through to failure until you do reach tetany. So because these cardiac muscle cells can't reach tetany, a state of full contraction, under normal conditions, they'll never go into that fatigue, right? They'll never fatigue and fail. So that's the significance, I guess, of that kind of slow calcium channel, is that we have this refractory period, right, that the muscle twitch completes during. So you can't depolarize the membrane again until down here, and the muscle's already relaxed again. So it can't do summation. You can't do summation, you can't do tetany. And because of actually not extremely well understood physiology, if you never reach tetany, you'll never enter that kind of fatigue and failure state. So that's kind of what, this is what successive twitches would do. The most rapid twitches you could have in cardiac muscle would look like this. Unlike skeletal muscle, right, where you have this short refractory period, when it contracts rapidly, it will do this stair-step summation, and you will reach tetany. And this will, if this is maintained long enough, this will inevitably lead to failure. Okay? So that's the significance of that L-type calcium channel in myocardial contractile cells, is that it prevents this rapid depolarizations of the cell membrane. Okay. Questions about that? Okay. That's kind of where we